Hello, welcome everyone. Um, this is the start of the opening presentation of the QuantumGrad Qiskit Fall Fest. We'll wait a few minutes for a few people to pop in, but yeah, we'll get started soon. People are filing in. We'll wait maybe 5 more minutes, I think.
Yeah, I think 5 minutes are enough. Checking the streaming, and we have a little bit of delay, but not no biggie.
Oh, welcome, welcome.
Welcome everybody. Nice to meet you.
Okay, why don't we go ahead and get started? So, welcome everyone to the opening presentation of QuantumGrad's Qiskit Fall Fest. Today, we're thrilled to have speaker Jesus Rincon Puche. Jesus is a mechanical engineer and physicist with a deep involvement in cutting-edge generative AI and large language models. He brings his experience as a former undergraduate physics instructor at the Universidad de los Andes and is
Yes.
an enthusiastic advocate for quantum computing. With his extensive expertise, Jesus is greatly positioned to give us a thoughtful introduction to the field. So please feel free to post any questions in the chat. Our team will do our best to answer as quickly as possible. And with that, why don't we go ahead and get started?
Thanks, Zach, for that beautiful introduction. Like he said, my name is Jesus Rincon. Um, I'm a physicist and mechanical engineer, but let's focus on the first part because, like he said, that qualifies me at the very least to give you an introduction to this very beautiful topic called quantum computing, which I assume a lot of you are interested in a way. And I'm assuming that most of you don't have that powerful background in physics. So the idea of this talk is not only for you to see what goes ahead when it comes to the mathematics and the concept behind it, but also to encourage you to leave a lot of questions and pursue a lot of information about it. So first, like he said, let me briefly let me briefly add some information to what Zach added. Um, right now, I'm working as a data engineer, focused, like he said, on cutting edge technologies for artificial intelligence. I also have a master's degree on condensed matter physics, uh, particularly in superconductivity. So I did a research focused on how to optimize the superconducting state on 2D materials. Why is that important? Because one of the forms that we can create a qubit, I'm gonna go briefly to it, is by using different types of quantum states. One of the most promising for this is one of the most promising states of matter for this is, of course, superconductivity, that is used primarily by IBM. A little bit spoiler for the head of DAC. So a lot of the concepts that you learn in these types of things, like condensed matter physics and so on, translate really good to quantum computing. So when I was invited by ex-colleagues of mine and recent colleagues of mine to, learn about this branch, I was like really thrilled too because it makes it mixes what I like, which are computing. We can do a lot of applications with computation. I'm gonna get that to that later. Yes, a lot of hints of what we're gonna talk in this presentation, and physics, which is something that doesn't matter how much are you aware or not, something that surrounds us every day. We can see it in our buildings, in our houses, and everything, but also in our computers and much more to that. So that's why I'm really thrilled to be here and be giving you this talk. Also, in a more personal side, I really like, of course, a lot of math related things, history things. So yeah, I'm more like a geek and a nerd, and I watch a lot of anime and stuff. So yes, I have my own musical project. I'm a guitar player and a singer, and we don't have time for me to give you a show, so sorry for that. But if you're interested in seeing my music endeavors, which I'm gonna need to be polishing more often, you can find me there and that at on Instagram. And yeah, from there you can find my music. This is shameless promotion. Sorry for that. But let's get to what we need. So, like I mentioned, we need to tackle some topics related to this beautiful thing. And that's why I'd like to call this our weird agenda. Why? Because quantum computing, quantum mechanics, rather than only quantum computing, the first time we encountered this, it may be a little bit puzzling, confusing. So we need to ground that level. We need to understand why quantum mechanics exist. So that way we can introduce one of the best things that are made that are used for this, which is the qubit, the quantum bit. And I love the qubit not only because it's the main unit of information for quantum computing, but also because it's a textbook sample, meaning that this is the most basic thing you can find on your undergrad class even to learn quantum mechanics, and the fact that it translates so good to real world applications shows the power of these things. And finally, of course, to encourage everybody here to not only research in physics and quantum computation and does a lot of complicated linear algebra, why I want to take some time to talk about some companies that work on this already, that have some SDKs, right? Because I know a lot of you are have a lot of enthusiasm for this, and some applications that we can have. Finally, of course, I will thank you all for being here and having a listen to this guy just being thrilled and excited about physics. And of course, like Zach mentioned, feel free to leave all your questions in the chat, and I will take my time, and I hope, along with Zach and the team, to answer most of these questions. That being said, let's get started. So, what is quantum mechanics? So, before we dive deep into that, we need to understand the rules of physics. So, we have four realms. We have like things when they move quote unquote slow, which is basically the speed that we're moving, and a big size. So, from an ant, which is big in physics, to a planet, and you suppose it doesn't move that fast, that's what we would call classical mechanics. That is mostly, not mostly, sorry, it is uh, explained through Newton's laws of motion. So everything we do, which is classical mechanics in a way or another, has Newton's laws of motion inside of it. But if we take that and we move way faster, close to the speed of light, to be more exact, we get close to relativistic mechanics. So we want to model galaxies, things that are close to the light from one planet to another. That takes relativistic mechanics. So everything that Einstein did, his famous theory of relativity, is in this box. But what happens when we do the opposite? What happens when we go to things that are way too small? How small? Most of you will be asking. Well, like some of you know already. If not, this is the point of this talk. To the size of an atom, of a molecule, even a particle. So we need quantum mechanics. And unlike classical mechanics and relativistic mechanics that are basically based on Newton's laws of motion, this is not um, driven by this. This is driven by some other theories that we'll deep dive later. But I think most of you heard because of movies, pop culture. I can't believe physics is now part of pop culture. But yes, this Schrödinger equation, uh, Heisenberg's uncertainty principle, and much more. This is all related to this. So this applies mostly to this size, to this atomic and particle size. But when we do the Schrödinger equation and the Heisenberg framework, we assume things are not moving that fast, even though they are. So that's why we call it. But if we need to go faster, that we need to take in account velocity and everything that can come out of it, which are basically a generation of new particles, properties of the atom that are not encapsulated by not taking in account the speed, we go to quantum field theory, or rather the big name, relativistic quantum mechanics, which is simply taking the speed that the atoms are moving in average, which is close to the speed of light, and adding that to find what I told you. So our main focus, of course, will be this part, because this is the only thing we need. And fortunately, we need to do it. But most of you will be asking, if you haven't taken any physics course, and no more physics course, why is so important? Why do we need to do like, well, quantum mechanics? Like, does it really change that much? Well, the answer is yes. Like I mentioned briefly, we have the main equation that relates classical mechanics is our Newton's laws of motion. So the first, the second, and third law, and like we all know, or maybe we're aware, they're basically the construction of like 95% of our model life. But and they take into account like mass, things like are really significant at this scale. Like the derivative of the momentum has mass related to it. So it's really microscopic, like I mentioned previously. But when we go to this scale, unfortunately, we need to change that paradigm because things are not moving the way we want to, or rather, this doesn't work the way it's supposed to work. So that's why we changed to the Heisenberg or the Schrödinger framework. One is basically based on matrices. That's why I put here linear algebra, which is something I want you to take really in consideration. And the Schrödinger framework, which is the calculus one, basically the famous wave equation. So what we use in classical mechanics mostly calculus. There's a disclaimer there, but mostly calculus, trust me. Um, we like I mentioned here, we have two options to work on: calculus or linear algebra, because the fact that these things becomes quantized, meaning it's not continuous, which is something that happens in quantum mechanics that I didn't write right here. Everything here becomes an unit. So you have like at this scale, you can have like units, but you can have half, thirds, fractions of whatever you're measuring. But at quantum mechanics, you don't have. At quantum scale, at atomic scale, you have like one atom, two atoms, a certain degree of energy, but you can have anything in between. This is something we find in the measurements. So, and because of that reason, using linear algebra becomes more convenient to it. But one of the reasons this is so weird for either undergrads and even people with experience to it is that classical mechanics is intuitive. What do I mean by that? Well, you can basically imagine and portray in your head like any problem related to this world, like say like the fall of this bottle. It's gonna go down. Your brain processes. If I start turning this, well, water will turn. Yeah, we may form a vortex, and that's another topic. But we can imagine the problem. Maybe we don't have the math, but we can imagine it. So our intuition to the real world uh, goes hand in hand with classical mechanics. But in quantum mechanics, however, that doesn't work. Why? Well, I don't know if some of you know it. Well, I think everybody has heard this by this point. But we know this thing of the wave particle duality of atoms. So that allows particles to do some weird things. Like, for example, if they are with the necessary energy, they may phase through a wall. So why? Because probability allows it, because waves can transmit and reflect and much more, unlike matter, like particles that would simply crash through a wall. Um, and that adds another layer to that. I mentioned that particles can go through a wall. I never said they will go through a wall, like I guarantee. But when I say that this bottle will fall, I am 100% sure it will fall. So classical mechanics is highly percent deterministic, meaning that if we technically know all the conditions for this system to work on, we can find all the characteristics they have, say position, momentum, anything that may describe this bottle. But when we solve quantum states, I'm gonna define later what that is, we will find a probability associated to each measurement. So we can find that the particle may go through a wall. That's a probability that can stay here. That's another probability that can go backwards. That's another probability. So now we have something that's not only probabilistic but random, because we don't know how or when one of these positions or states, which is the common name for quantum mechanics, we um, will be in. There's a lot of things that we can do in real world to guarantee that what we want is what will happen, because there's a lot of application in quantum mechanics in real world, like for example the transistor, which is the main electronic tool for our modern lives, so our computers, cell phones, TVs, etc. Everything that we're using to communicate right now is not only a mixture of classical mechanics, but it's also a lot of quantum mechanics. So, no, so quantum mechanics is already really useful and really known in real life, but now we need to get it to another realm. But before we talk about quantum computing itself, like I mentioned previously, we need to have a little bit of vocabulary. So, like I mentioned in the last slide, we can use either linear algebra or calculus. For the sake of how the quantum computing is designed, we're gonna go to the linear algebra frame. Now, I'm assuming most of you have an engineering background, scientific background, so all of you know what a matrix and a vector are, right? So when you apply a matrix to a vector, you will find something and a different vector. But when you have an eigenvector of that matrix, which is a vector that represents part of the space, and you apply that matrix, you will find an eigenvalue and that same vector. The eigenvalues and eigenvectors are something that arises all day long in quantum computing and quantum mechanics. But they're basically our kids. So if you want to do quantum computing or quantum physics or whatever, will be like your daily thing in one way or another. Of course, there's a lot of more complicated topics that I'm going to touch in this talk that if someday we probably find a way to add more inside the linear algebra for quantum mechanics. But overall, you need to remember this. We're basically going to work with matrices and vectors that are related to each other by an eigenproperty. Now, that being said, let's start getting inside this vocabulary. So I'm pretty sure that a lot of you have seen this type of nomenclature. Um, what are you? This is how we represent the state, like I mentioned, and this will represent a property of the particle or molecule that we're modeling, say the position or the energy or whatever we want to measure. But what are they in the terms of this little towards it here, linear algebra? Oh, this is a vector, this is a vector, and this is a vector. Now, so if this state that represents the total spin of the electron, I'm going to define that later if time allows me, because it's really important for some properties, then this represents some amplitude uh, times the offstate vector plus another amplitude or coefficient for the downstate vector. So what is this in linear algebra, if you remember like your classes? Well, this is basically a linear combination. It means that the total state in my electron will be the linear combination between the offstate and the downstate. And these coefficients will tell me how big that is. But let's go back to the slide. I mentioned here random and probability. So that means that this is related, or is the probability. The answer is related because this is a coefficient that is a complex number. And complex numbers can't be probabilities, but fortunately they have a norm, a square norm to be rather. So when we find the square magnitude of this value with concepts that unfortunately are not with a simple concept that I didn't explain for this talk, we will find the probability of the state to be either up or down. Now, I did mention some things later, but I'm going to get to that later. Now, we need to measure this, right? We need to find the total spin of this example, for example. So what we need to do, we need to make a projection of this state to something that measures our life, say a detector, a beam, something that interacts with the spin. And we will do this projection. So this is a column vector, this is a row vector. So this is basically the general representation of a dot product, or more generally, the inner product. What's the difference between the inner product and the dot product? Well, uh, one basically takes in consideration only vectors, and the other one takes consideration anything that has like vector properties. So in this case, we can say that the phi state is an operated state, meaning that we measure that something up, meaning that it can be phi times an observable. What is observable? What I just told you. Something that measures this, like a being, a machine, whatever. And we then project it to what we expect, and we will get one of these coefficients, in this case, squared. So we will get the probability associated to getting what we want. So let's say that we want to measure up. We will say that T is up, in this case, and we put an operator such that this gets up. So this A here is going to be this coefficient squared. And the value of this coefficient will be the probability of us getting that value. Now that we know this, let's use, like I mentioned, one of the best examples in life, which is the qubit. What is the qubit? So the qubit, or the quantum bit, is basically the basic unit of information in quantum computing. And it works just like a bit. It can be a 0 or a 1. For that reason, this is what we call a two-state quantum mechanical system, meaning that it can be either 0 or 1. And before we measure, we are in this thing that we call, and we are in this linear combination of the possible states. In this case, we can say that up is 0 and down is 1, for example. So whenever we have a qubit that we haven't measured, it can be simultaneously in up and down. And what is that property? Well, that property is what we call superposition. And superposition, fortunately, you don't need to know quantum mechanics to understand it. You just need quantum mechanics to understand measurement. So what is superposition in waves? Well, it's basically when you take in different waves in different frequencies and start adding them up. For example, my voice, your voices, the instruments you like, there are superposition. Say a guitar. You take a guitar and you play a chord. A chord has different notes. Has an A, say a C major it has a C, an E, and a G. And you play that, and it sounds like an E and as a C major. And that's a superposition because it's taking all the frequencies related to the C, summing it to all the frequencies related to the E, and summing it to all the frequencies related to the G. And that's what superposition is. It's as simple as that. Now, so this thing that we have here, it's simply a superposition. Now, the difference between classical mechanics and quantum mechanics is that when we are in classical mechanics, when we do superpositions, like my voice and like the core I explained, you're gonna listen or you're gonna absorb all this information that is superposed. But when we are in quantum mechanics, we're only gonna take in consideration one of the states. What? Which one of these frequencies? Let's call the possibilities frequencies. Which frequency? The one that is most likely to happen, or the one that the systems allow. For that reason, superposition is a really powerful tool. However, I did mention here that we have like these coefficients for complex amplitudes. And why is that so important? Because complex numbers have a really beautiful thing to them, and is that basically they can create a circle or a sphere. So all the combinations that we can be represented in this type of spheres. For a qubit example, this is the block sphere, and a block sphere is a summary of what I just told you. Each point inside this sphere, it's a superposition between the 0 and the 1. Now, even though I mentioned that quantum mechanics works on a quantized state and on a finite number of states, that doesn't mean that the superposition is finite. So how many possible points can we have inside this sphere? Answer is infinite. So a lot of information is pre-processed inside of it, meaning that whatever we want to measure inside the qubit, either the result of the 0 or the 1, are simultaneously living here. And until we measure it, however, we're gonna get a result. But some of you might be wondering or thinking, Jesus, you're mentioning this, and this sounds really interesting. However, based on what you said, this is random. So every time we measure, um, it can either go the measure I want or something else that I never expected. How can we deal with that? Well, we fortunately have interference to help us with that. So what is interference in classical mechanics? Again, it works the same in both realms. Well, interference is basically when you add two waves of information, you can either increase the amplitude of the wave you want or decrease it. So what is interference in quantum mechanics? The same thing. When you interfere two signals, you can either make one big and the other one small, and the other one small. So what is the importance or the power for this interference that we can start adjusting our systems to this sphere to be in the point that we need to. So say we need a one because we already know the experiment or the measurement, we can start using interference by when there's an example in Qiskit that I may get to later using the grid, but we basically will do some operations to guarantee that one is the one that has more prominence in our measurement, and so much and so forth. But now, and now that that's sort of the way, I I hope that some of you are making this question, which is, okay, this is cool and everything, but why is the gist? Like, what's the funny part? How does this add to my already powerful classical computing that already does like a lot of complex things like say finance or LLMs or anything like that? How can I add using quantum computing? Well, partially we have entanglement. Now, what is entanglement? This is a complex thing to explain, so bear with me in this one. I have this analogy that hopefully gives a gist to that. So imagine you have a twin. That twin and you are really, really like bread and butter. You guys spend a lot of time together. You already have like this brotherly bond that cannot be explained by anything except your love for each other. And in one of those, and on one day, your twin decides to go live on Japan, so the other side of the world. And communication there becomes complicated. And one day, you're like walking to your home, and you have like this feeling like your brother is sick. Because you're too busy, say on work, on school, you write your mom asking her to please text or call your brother or sister to see how they are, and she does that, and turns out he they were sick. So that's loosely how quantum entanglement works. Because when you create a state like this, you create this with two different spins. So we have like this spin one, this spin two, not this superposition, but rather like two, like like two vectors like this. And when we created the system, they already began with some properties. They say they have like this Taoist level of energy, a spin. I'm gonna define that later. I need to define that later for you guys. Much more. And you put them really, really far apart. So, since they're part of the same system, we need to always guarantee that all the initial properties are conserved. This word is like the most important word in physics, conservation. And whenever we do a change in one place, say we have two electrons, and we have spin. Now is the time to find spin. What's spin? It's called the spin. It's called the inner angular momentum, which is basically like an inner magnet that electrons have. So when we create a system, one spin is up and one spin is down, because we need to always guarantee that for electrons, the total spin is zero. That's what they're opposites. And now we've taken them far, far, far apart. The moment we change the spin from one to the other side, immediately, because of this conservation, this one needs to flip. It's like the system for being far apart, quote unquote, changes the properties. Now, when we take qubits and we start to entangle them, all the information they're processing starts to be shared among them. And because of this entanglement, the way they process this information starts to grow exponentially, allowing us to process more information. And at that, the superposition state that we have, that we can start doing some interference by doing some operations, we can start having a system in computation that can process a wide and vast amount of information. That's why I created this little table to explain the differences between the bit and the qubit. I already mentioned this one. We already, like in bits, we only have like one or zeros, and that's it. And that we don't superpose until we measure. However, unlike bits, qubits scale in a power of two rule, meaning that, say, you have two bits, but if you have two qubits, they have the information of 4 bits. You have, and in order, if like you have 3 bits and that's it, but if you have 2 qubits, you have 8 bits of information or a byte, and so on and so forth. So they start exponentially increasing the amount of information they can process. Why is that? Because of what I told you previously, because of this property, entanglement, because they start to become entangled between each other. Now, into the gist of this. This sounds really fun and stuff, but some of you may be wondering, like, do I need to change my paradigm to start working on qubits? Unfortunately, at least so far, like today, 2024, the answer is yes. Because most of the logical gates on Boolean algebra, tables of truth and false, and on qubits, there are still the equivalents of these tables of truths and so much more, but they are not looked by the rules of Boolean algebra. They're looked at on the rules of linear algebra. So we have matrices and vector spaces that will represent all these operations that we have. Our current bits of information, like the ones we're using now to, you guys seeing me and knowing all this information, are basically current inputs that poorly explain every time a computer does something. It's either current getting in or getting out. However, like I mentioned previously, we can create qubits with different ways. Say electrons, in this case, using the spin, the property I explained you, this in this angular momentum. We can use photons, so we can use light. We can use superconductivity. They have these things called Cooper pairs that are basically a really type of two electrons that can share spin. It's really more. It's really a little bit complicated for this for me to dwell on that, but it's really useful. And that's the main unit of information for say the quantum computer in IBM, and much more, and so forth. Now, the thing with this is that unlike this, which is multi-purpose, meaning that we can do a lot of things that we want to say, some machine learning, video game, etc., whatever we want to. Um, qubits, unfortunately, for like at the time being, are really more focused on. Say the say qubits for photons are more for quantum information, or I don't remember which type. Sorry for that. The superconducting ones in IBM are really more focused for optimizing rather than just doing machine learning. And the ones of the ones of photons by Xanadu actually can be used for machine learning. Now that I remember, and like I mentioned, this thing scales too big and it really processes a lot of information. So your classical computer will always be better for simple processing, say summing, um, quick calculations and stuff. But if you want to do something bigger, something that's really out of the capacity of your computer, which I know that you guys know that there are a lot of problems for that, just not only on machine learning, but also on fluid dynamics and materials and stuff, that unfortunately our computers can process, then that's when quantum computing will thrive. Why? Because it has the facility to process a lot of information. Like I said, this scales linearly, and this scales exponentially. So, of course, this is the idea. But there's another con to qubits. Our classical computers are really good, well designed to work on these temperatures, on this state, like say at 1 atmosphere of pressure and like 20 degrees Celsius average for room temperature, and so on and so forth. But I didn't mention this because I was waiting for this part of the talk. Quantum systems are really sensitive. Why? Why is that? Well, we're still trying to figure this out. So whenever you have like a superconducting system, they're like in average like 10 Kelvin. That's around minus 260 degrees Celsius. So really close to absolute zero, basically. And whenever you go higher than that temperature, I believe it's around like 15, 20 Kelvin, uh, entanglement starts to disappear. Um, Superposition starts to be outside of everything. And when that happens, there's a name to that. I forgot the name of this chaos and temperature. Sorry about that. When you get reach this temperature or scale, um, quantum properties just disappear. So that's why we need to do a lot of effort for this. Now, I know what a lot of you will be thinking. So if this is so sensitive and so easy to destroy, then why are people putting a lot of money to it? Let me get to that in the IBM's part, but let me tell you that we found recently, like in the mid 20th century, ways to break this rule, or rather re-scale this rule, for example, in superconductivity. Now, that being said, I hope this gives you a panorama of whatever we have here. Like I said, it's a lot of information. I apologize for not dwelling deeper inside the mathematical physical concept. This, I just want you to give you an overview of this for you to take more classes on it or research on your own. And I hope that you find this at the very least interesting, because like I said, there's a lot of people working on it, and we need to take advantage of that. So, like I mentioned, I've done a lot of times during this talk. We have IBM. This is the superconducting computer they have. This thing looks huge, and it is. So, how does this work? Like I mentioned, it works by superconductivity, and like I mentioned previously, it needs to go in a really low temperature. So, this computer here has a lot of knobs and a lot of tubes that they're which a certain liquid goes through. Which liquid is it? Well, it's liquid helium, and that thing is not only really hard to make, it's not also really expensive to maintain. It's really also really easy to heat up. So this computer is basically isolated from the world to guarantee that the helium doesn't heat up, that everything keeps cold, and much more. And they already created systems for that to go increasing more qubits, like you guys, I think you guys already are aware of. I don't remember how many qubits they have, but they have like they are aiming to have over a billion operating quantum circuits by 2033. And but that doesn't mean that we can do things already on our own for using IBM. They have a system called Qiskit that again I said this a lot, but I need to emphasize on this. I think you guys are aware of Qiskit already, where you can create your quantum circuits. Now, if you've been already in Qiskit, you will see that there's like a mesh where you can add like boxes and you can and you see a lot of the ket symbol that I showed, like the vector symbol I showed you. Well, the boxes are operators, and they start to do what I told you. And there's a symbol to entangle them, so it becomes really graphic design for your circuits. But if you don't like graphic design for your circuits, which is highly understandable because you're probably more used to writing code, and this SDK has Python packages, so you can install on your computer and write your code, which will basically do everything that I told you about this graphical interface, but by code. And you can start creating your systems with virtual qubits to start like scaling or processing or imagining how much qubits will you need in the future for a new process. Which research topics we have? Give me a couple of minutes to that, but trust me, there's a lot of topics that you can work on. Xanadu, it's another quantum company. They basically focus on creating these quantum chips that are basically qubits done by photons. They're like the leaders right now on quantum machine learning. They have this Python SDK called Penny Lane that you can install on your machines, and not only it will give you access if you pay, of course, to their circuits, but if you want to your code and connect it to IBM or some other of the companies that I'm not measuring that I'm not mentioning today, because there are a lot of companies that do this, you can do so. And again, feel free to install Penny on your computer and start working on it. It's really Python based, and works mostly on decorator side. So you will take like your circuit, create as a decorator, and start adding more information to it. And again, you can use it to start imagining what projects or how many qubits you will need in the future when this is more feasible for big scale projects for you to use. And and again, there's a lot of more companies that I'm not mentioning, but there are a lot, and they're basically just like IBM and Xanadu working on research for quantum components or anything like that. Because software is something that's right now something that we can start designing using their SDKs or pen and paper, however you feel like it. Probably most of you are like have this background in computer science, so please feel free to write code. Now, you saw this computer, right? Like this is humongous. It's not something you can have on your room, like our PCs. So so for that reason, these guys know, like Google, Amazon, and Microsoft, they guys know that this is really, really, really profitable. That's why they're also investing a lot on that. Microsoft has its own language called Q Sharp. That's basically like the SDK on Qiskit, but it's their own language based on C sharp, and they also created a Python SDK because quantum rules nowadays. Um, I forgot the name of Circuit. Google has Circuit, which again has their own SDK and their own development and their own computers. These guys have their own quantum computers being built for these processes. And Amazon, who Jeffrey Bezos loved physics because he was a physics major prior to founding Amazon. He doesn't create. This may be misinformation from my end, so apologies for right now. But I think he's mostly connecting providers to the cloud. Why do I mention this? Because Google and Azure not only provide their own services with Q Sharp and Circuit, but also they connect you with our providers like Xanadu and IBM. And you can start working on the cloud, so you take a lot of the pressure of having your own computer. But I think I said this a lot. This probably is not the cheapest thing to maintain, and this is definitely not the cheapest thing to maintain. So when you work on the cloud with these systems, it's gonna be really expensive. So be aware of that. But it's something that a lot of people are working on, and yes, there's a lot of things that people are working on, because that's how I want to close this presentation for you guys. I mentioned that we have a lot of things that we can do with quantum mechanics and quantum computing. And in this thing, in this diagram, this beautiful diagram I have here, um, quantum computing is essential for most of this. It's for you guys that that you may be interested in it. Like you may heard that quantum computing, when the time given, will probably break all our keys. Yes, because of what I mentioned about entanglement superposition. So these two properties allow us to test simultaneously all possible combinations to break the key. So we need to prepare ourselves for that. That's why we have the post-quantum cryptography. A lot of companies like Amazon and some banks are already investing on this. But say you wanna make sure not only does break, but you wanna create new keys using quantum computing because, like I said, this is highly 100% random things you can create for this. So you can create new keys. Um, but say you wanna have fun and because you like data a lot, like I do, and you wanna see how much quantum can improve on neural networks. So let's create our quantum neural networks right now. For example, Xanadu and Qiskit give you the ability to do hybrid computing. So you can have your layer in your network that has all the classical processing, but also you can have one or two layers that do some quantum processing to these machine learning algorithms. For what? For them to be increased. If you're like me, that you work on physics and you already work on materials, for example, quantum materials is also something that's really highly researched nowadays because, like I mentioned, and this was part of my thesis, we're trying to find a way to sustain superconductivity at room temperature and atmospheric pressure. There's a lot of research and advancements to it, and that's why IBM is betting for the superconducting computer because it's like the one that goes way ahead in research compared to the other technologies. But I I don't know if you guys wonder, but I only mention like this works on software and mathematics. But shouldn't we have like properly quantum chips and RAMs and devices for that? Well, yes, and we should indeed. And that's one of the research topics. And so much more that we can research on. So this is a really like new topic overall. And unfortunately, physics is one of the main reasons, not because people are not investing a lot to it. A lot of people are investing to it, not only IBM, not only colleges, not only governments, and much more. It's just that physics is really this complicated that doesn't allow us to fully go beyond that. And we're walking this as a slow pace race, like a marathon. You need to keep your energy, keep your enthusiasm, and keep your stamina to all the process. So when we reach here, we're all prepared. My invitation to all of you is firstly, if you find this interesting, thank you for listening to me. Now we're gonna go to the QA. And secondly, um, know that there are a lot of things that we can learn and do with this beautiful topic. Again, thank you very much for listening to me and hope you enjoyed this talk.
Thank you, Jesus. That was really good. Uh, Given the stream has a bit of a delay, if you could talk on some of your work and some of the things that you've been involved in quantum computing, that would be a good interplay before the live stream catches up.
Yeah, of course. So um, right now I've worked in two companies relating basically trying to lead along some other colleagues with higher level, introducing this to the consulting world. Basically, in my last job, we were doing POC focused mostly on quantum machine learning, which was this example I gave you of doing neural networks or layers of classical computing and extra layer of quantum computing to enhance the processing of the machine. We also were trying to do a POC. Unfortunately, I couldn't finish this because I was switched from jobs at the time. But we were doing a POC for finance. There's a lot of papers, a lot of information using Fourier transformations and much more that we can use for finance. There's a paper on that. I forgot the name. I owe you that paper, sorry. But there's something that's inside some of the wall, and this was led by Sanadu, and I believe IBM was also trying to copy this paper, like any good research. And here at IBAM, which is my current company, I'm also trying to, again, we're trying to lead this to be a part of the corpus of the business. Uh, no projects whatsoever, only focus on POCs. We have a colleague of mine, he's not here, his name's Maxim. He's really crack and he's doing some things for detecting spam, neural networks on his own as POC that we may or may not, that depends really much on something outside our resources, to present to the higher ups to see if they're interested to apply this to companies. With, of course, the disclaimer I just gave, which are this takes time, this is really expensive, this is not gonna go from one day to another. And on my free time, of course, I'm trying to do some POCs related like this business thing I told you, probably going back to materials. And also I have a like for fluid dynamics because of my first major. So, and I've read some papers regarding how to use quantum computing to characterize and to find and to characterize and just to characterize turbulence, which is something really complicated in classical mechanics.
Very interesting stuff. So we'll wait a few seconds to see if anyone has any questions, but if nobody does, then I guess we'll close it off there. I think we're good. Yeah. Thank you for your presentation, Jesus. That was really very interesting and very informative.
My pleasure, Zach. Thank you for having me, and hope to keep and hope to do more with you guys. If
Yes, we hope
if
to
you
do
should.
that in the future. All right. Have a good day, everyone. Thank you for joining the
Have a good
stream
day,
and
everyone.
see you at the next one on the